At first glance, it might seem logical to think that a small boat, being lighter, should be faster than a huge cargo ship or a 300-meter cruise ship. However, when we observe reality at sea, the opposite is true. The giants are the ones that glide most efficiently and reach surprising speeds. How is it possible that tons of steel can move so elegantly, while small boats are buffeted by the waves and struggle to move forward? It all has to do with the laws of physics, naval engineering, and something experts call the relationship between length and speed. Large ships not only have more powerful engines, but their sheer size gives them a natural advantage over the waves, reducing drag and improving stability. This phenomenon, although it seems counterintuitive, is a masterpiece of modern engineering and the science of fluid motion. Furthermore, water does not behave like air. Its density and the way it moves around the hull determine a vessel's theoretical maximum speed. A small boat creates waves and turbulence that slow its progress. A large boat, on the other hand, flattens them with its mass and length, cutting through the water with an efficiency that would seem impossible if we did not see it with our own eyes. But to fully understand this phenomenon, we must literally immerse ourselves in the principles that govern modern navigation, fluid physics, hull design, and the magic behind marine propulsion. A boat's speed is not measured solely by the power of its engines, but by how the water reacts to its passage. This is where a key principle comes into play. The Froude number, a formula that relates a boat's speed to the length of its hull. According to this law, the longer a boat is, the faster it can travel before reaching its natural speed limit. To explain it simply, when a boat moves, it generates a series of waves at its bow and stern. As it accelerates, these waves become more separated until the bow wave coincides with the stern wave. At that point, the boat literally begins to ride its own wave, creating enormous resistance. This speed limit depends directly on the length of the hull. The longer the boat, the larger and more separated its waves will be, and therefore the greater its speed before reaching that critical point. That's why a 10-meter yacht may struggle to exceed 15 knots without disproportionate energy consumption, while a 300-meter container ship can move at 25 knots efficiently with less relative resistance. It's not magic. It's pure physics applied to naval design. Resistance is also divided into two main types: friction resistance, caused by contact with water, and wave formation resistance. Engineers spend years designing hulls that minimize both, optimizing every curve and line to achieve the perfect balance between speed and stability. That's why modern ships look sharp at the front and wide at the base. They are made to cut through the water like a hot knife through butter. The second major difference between a small ship and a large one is in propulsion. Large ships have colossal engines designed not only to move the mass, but to do so with surprising energy efficiency. For example, a container ship's main engine can weigh more than 2,000 tons and generate more than 80,000 horsepower, all while running at low revs, which reduces wear and tear and maximizes thrust. Unlike a car engine or a speedboat, marine engines are designed to work with continuous thrust, not rapid acceleration. This means that their design is geared towards maintaining a constant rate of travel, taking advantage of the ship's inertia and size to maintain speed with less energy expenditure. Propellers also play a crucial role. On small boats, they're usually lighter, rotate at high revs, and lose efficiency due to cavitation, bubbles formed by pressure. On large ships, on the other hand, the propellers are enormous, several meters in diameter, rotate slowly, and push a much larger mass of water with less loss. This combination allows a ship weighing hundreds of thousands of tons to move smoothly, without the need to increase speed abruptly. The shape of the hull, the weight distribution, and the engine power are calculated down to the millimeter. And although these giants may seem heavy and slow, their design makes them true champions of efficiency. They can move more cargo at higher speeds while consuming proportionally less fuel per ton transported than a small ship. A large ship is not only faster, it is also more stable, and that stability directly influences its speed. When waves hit a small ship, it bounces, loses energy, and needs more power to stay on course. In contrast, a large ship barely feels the waves. It cuts through them with poise, maintaining its momentum without interruption. In addition, inertia plays a key role. The heavier a ship is, the more energy is needed to set it in motion, but also the more energy it stores once it is sailing. That accumulated kinetic energy allows it to maintain its speed with less engine effort, something that small ships cannot take advantage of. Another crucial aspect is energy scale. A small ship needs an engine that constantly overcomes water friction, while large ships use their own weight and wavelength to float over the waves with less resistance. In practical terms, large ships are not only faster, but also more efficient. They can travel thousands of kilometers carrying tons of cargo with surprisingly low fuel consumption per unit. Even cruise ships, those floating cities with swimming pools, movie theaters, and restaurants, can maintain speeds of 20 to 25 knots thanks to a combination of power, aerodynamics, and hydrodynamic stability that small recreational boats simply cannot match. A boat's speed depends not only on its engine, but on a complex combination of physics, engineering, and design. Large boats are faster because the very nature of water favors them. Their length allows them to overcome the barrier of waves. Their mass gives them stability, and their power translates into continuous and efficient movement. It may seem paradoxical, but heavier ships are also the most graceful in their movement. While a small motorboat struggles against each wave, a colossus of the sea advances unperturbed, proving that in naval engineering, size does matter a lot. The next time you see a huge ship passing on the horizon, remember that behind that apparent slowness, there is a perfect balance between power, physics, and precision. They are the true titans of the ocean, slow only in appearance, but built to dominate the waters with an elegance and speed that only science can explain.